All right. Hi, everyone. So what I'm going to do right now is I'm going to talk you through how and why we're generating two graphs for the acceleration due to gravity lab. Right? I'm going to share my screen, and there we go. Okay. So if you go back to the very beginning of the lab, which sometimes when you've been doing something for a long time, it's a good idea to go back to kind of like when you're writing, you go back to your thesis statement, go back to the problem statement to see what you're actually supposed to be doing here. So your goal for this lab was to graphically determine a value for acceleration due to gravity. Now, hopefully by now you know that acceleration due to gravity is 9.8 and you are not discovering that. You really are, and we're just looking to get the magnitude, by the way. You're verifying it. Okay, we're looking to see, could you generate a data set that verifies that this is in fact our acceleration due to gravity on Earth within a reasonable degree of error. So what you had to do was you were limited by only using distance and time data. Most of you, I saw, had a data table of some kind, because that should make sense. If you have to graph something, you're going to need to have a data table. I want to make sure I'm recording. I am recording. Okay. So most of you have a list of times in seconds. And then you have some kind of a distance. You could have that as a D, you could have it as an X, you could have it as a Y. It really doesn't matter in this case because since you're just moving in one direction, your distance and your displacement are equal to one another. And then you have a bunch of data for that. Once you have that data table, you should be generating your first graph. Now, I would suggest that you start with 0, 0 as your first data point. And the reason I would suggest that is that's going to shove your data down to shove your curve down. It's also a true statement. At time of 0, the displacement is 0. So you can use it. Then when you plot your data, what you're going to see is you kind of get something like this. And if you go into your sheets and you do use a scatter plot, and then you put in a trend line, your trend line will automatically show up as linear, and you're going to want to change that. I'm going to do a second video today to help you with the graphing because it looks like you don't all necessarily know how to use sheets either. So we'll make sure that we get those skills up to par here. Also, you should have units. All right. So what you can do is instead of doing a linear fit, you can do an exponential or a polynomial. And I would suggest you try both and use the one that fits better. When I tried it with one of our group's data, the polynomial was the best fit. That's going to put you something like that. And that's about what your first graph should look like. So the problem with this is that your slope is constantly changing. All right, if I were to draw a bunch of little tangent lines, obviously this is not a great tangent line because I'm not even hitting the curve, but I'm trying. If I were to draw a bunch of little tangent lines, what you can see is that velocity is increasing. And that's what should be happening because you know gravity is accelerating it as it's falling. But using that slope to try to get your value for acceleration due to gravity is very difficult unless you understand calculus, or if you wanted to get a whole bunch of little slopes and then graph velocity versus time. You could do that, but then you're moving away from the purpose of the lab, and the purpose of the lab was to use position and time data. So I'm going to show you what else we can do. Think about it like digging through your toolbox and you get yourself stuff and you're like, all right, what else can help me here? What's always going to help you in this class is using your equations as your guide. It's like Jiminy Cricket. Jiminy Cricket is like uses his conscience for his guide. We're going to use our equations and also our conscience. But if I look at this kinematics equation, remember we started here for our linear acceleration in the x direction, and then we talked about how we can apply that equation to free fall. And really the only difference is that we're going to use a y and a g instead of an x and an a. We could use the same variables. In this problem, from the beginning of your data, wherever you started and however you did this, the beginning of your data, you were dropping a ball or a Barbie or whatever you were dropping. So that means the initial velocity of your drop was 0. So I'm just going to get rid of that. And then that allows me to look at this equation and look to see what the relationship between change in position and time actually is. And if you look at this simplified equation, even if you look at it without simplifying it, what we see is that y, your change in position, is directly proportional, that's what that little symbol there means, to time squared. Okay? So if we think about linearizing this and we think about how can we use this equation to help us verify g, I'm going to, not graphically, algebraically rearrange this equation to solve for g. And if I do that, I'm going to get g is equal to 2y over t squared. All right? When you think about that, remember we're graphing, and you all did something very similar to this when we did the gravity lab earlier on in the year. Think about your equation now as your guide to an x and a y axis. If instead of graphing just position and time, if I graph position, your distance, or your height of fall, whatever you want to call it, over time squared, watch your units there because now it's seconds squared. If you can't figure out how to square something in your sheets, put a caret and a 2. Now what's going to end up happening is if you take the original time data that you collected here and you square all of those numbers and you graph it, the mathematical relationship according to our equation between position and time is that it is proportional if we do position versus time squared, and you should get a linear slope there. Okay, now if you notice, I'm not graphing the 2 because we don't graph a constant, but we can't just forget that that 2 exists. So what I'm going to do is I'm going to get my slope here. All right, the symbol m is slope. Remember that your slope is y over t squared. There's not really a significance to that, except for now if I do slope time, not slop, slope times 2, that should give me my value for g. Okay, another way of saying that is that the slope is half of g. And then that should be close to your 9.8. So your slope when you do your position over time squared really should be around 4.9, somewhere in there. And again, you're doing this not necessarily with the equipment that we have here. So I'm expecting that your data is not going to be perfect this year, and that's okay. That's where we talk about what we could do to make things better, and that's what researchers do. We collect information, whether it's in science or psychology or education research. We say, here's the situation. Here's my recommendations for what we do in the future to make things better. And here's my sources of error. We were dealing with air resistance, my reaction time, those types of things are legitimate sources of error for you guys in this lab. So going back, the first graph you have should be position versus time. You should get a polynomial or an exponential fit. Probably the polynomial is going to be the better fit. I would like you, when you do that, to display the equation, and I'll show you how to do that on the video tutorial for making a graph in Sheets. I'll do that one today as well. Might not happen until later on in the day, but but I'll do that one as well. Once you have that first graph, then if we use our kinematics equation as our guide for thinking, what we see is that our position, our height, is proportional to t squared. So if we graph position or height and time squared, we should get a linear fit, And according to our kinematics equation, rise over run times 2, if we multiply our slope by 2, we should get a value for acceleration due to gravity. All right, give that a try. Hopefully tomorrow we have better Wi-Fi, and then we have tomorrow and Wednesday to tie this up and answer questions and really help each other out with this. Hang in there, you're doing a great job.